like this to being over-organized and cycling and doing a lot of extra things. So nowadays we use heart rate data, we use power data, we use GPS, we do questionnaires to monitor and see how we can fine-tune and monitor a cyclist. And one of the other things that we look at as well is heart rate recovery, or maybe even more correct, the rate of increase in heart rate, what we've heard before today at this conference, and heart rate variability as well. And that's what I'm going to be focusing on today a little bit. Why is it so interesting to look at heart rate and changes in heart rate or heart rate variability? It's really interesting because it's basically mainly being regulated by the autonomic nervous system, which exists out of a sympathetic and a parasympathetic branch of it as well. And that has actually been influenced by many factors. So not feeling well, not sleeping well will all reflect on your autonomic nervous system. And then from that, we use proxies as heart rate by the rate of increase or the rate of recovery after a submaximal exercise, or heart rate variability to see how imbalanced is this system or isn't this system. So we all know with increasing exercise intensity, we see an increase in sympathetic activity that drives the heart rate up. We see a reduction in parasympathetic activity, so we can use that as a measurement, as the rate of increase in heart rate to see how the sympathetic and the autonomic nervous system responds. And vice versa, we can also look in the recovery phase directly after submaximal exercise, how these two respond. If we talk about heart rate variability itself, then we mainly talk about the differences between the RR tops itself. So if we look at a general ECG, we see that those B2B differences always differ quite on a regular basis in rest. And the more we are stressed or the more we exercise, the less variation we will see in that parameter. We can measure those differences, and then we can calculate them over a time frame, and then we can analyze them basically in two different ways. We can look at different frequencies, what we call the frequency domain, and we can look at a time domain spectrum as well. And then from that, we can derive different parameters. Within the frequency domain, we can talk about a frequency, what we define as a very low frequency, a low frequency, a high frequency, and then Debré-Tourette as total power and the ratio. And then in the time domain, we can look at RR intervals, triangular index, and something which is called RMSSD, where I'm actually going to be talking about today. And the RMSSD is the square root of the mean squared successive differences of the adjacent RR intervals. So I'm happy that's out. So I'm just going to call it RMSSD from now as well. The presentation is going to go far too long. So I'm going to be focusing on that. What is the criticism about heart rate variability? Well, mainly the criticism is a lot of people say it's not practical enough. And it's not practical enough because it always generally needs to be measured under very controlled conditions. So you need to either lie down in a very rested condition or sit down in a controlled position. And the measurement is relatively, generally very long, 10 to 20 minutes. We're shifting now towards having shorter periods of time. But for elite athletes, this is very hard to implement in their daily structures. In addition as well, because we're measuring it in rest, the variation in heart rate variability is big, which we want, but it also on the other side creates a problem that it's very hard and not as sensitive to detect meaningful changes over time. So with this in mind, and with the development in heart rate variability now moving towards being able to measure heart rate variability over much shorter periods, we came up with a question, are we actually able to measure heart rate variability over very short periods of time, and then specifically using the RMSSD method? So the aim of our study was, can we actually capture heart rate variability or RMSSD over ultra short periods, and I'm talking about anywhere from 30 to 60 to 90 seconds, and directly after a standard supplemental exercise, and is this measurement reliable or not? If we can be captured, is it reliable? Does it mean anything? Is there any relationship between the measurement that we make and any of our cycling performances that we want to look at, so peak performance and endurance performance? In addition, as well, is this then similar in male and female cyclists, or are there differences between the two? So do we need to differentiate between them if we start using it as one of our parameters to monitor to monitor cyclists and fine-tune training? So two parts of the study. The first part, we conducted a submaximal test called the LSCT. I'll tell a little bit more about that now. We looked at heart rate variability at 30, 60, 90 seconds. And then the second part, we looked at a relationship study, and we basically conducted a submaximal test followed by a VO2 max test. And then basically a week later, we asked the guys to come back in, another LSAT test, and we performed a 40-day time clock test, which allowed us to see if there's any relationship between the heart rate variability measurement and the endurance and peak performance. We use the LSCT, which is a sub-maximal test, which is fixed on heart rate. It consists out of 3 stages. We ask for cyclists 6 minutes to cycle at 60% of max heart rate, 6 minutes at 80% of max heart rate, and 90% of max heart rate. During that, we collect power data in the different stages. We collect RPE, we collect cadence, and a few other things. But what I'm going to be focusing on is mainly that last recovery part, where we collect heart rate decrease, so heart rate recovery data, and where we collected the RMSSD data as well directly after the exercise. If we look at an example of that data, you can see that at the lower intensity, so it's almost a mirrored part as well, you see lots of variability, which coincides with the lower exercise intensity. If we go to 80%, that variability comes down substantially, and if we hit 90%, there's barely any variability left in that heart rate, which is logical with the high stress that we put on the human body. The thing again, what I'm focused on is that little part and see which part of that is mostly reliable to look at heart rate variability. Quick bit of background on our cyclists. We had 14 cyclists in a reliability study. We had 15 males and 20 females in the relationship study. They ranged from being reasonably trained to reasonably well trained. So we talk about watts per kilogram. On average 5.1 in the males, but ranging from 3.8 to 7.1, so near elite. Female cyclists 4.2 to 5.2, so quite a bit of a range of different cyclists in that group. If we look at the reliability data, and we were able to capture the heart rate recovery data from that as well, we can clearly see that the highest reliability that we were able to achieve were within the heart rate recovery, so the standard method that we mainly use after exercise, and 60 seconds RMSSD data, which we log transform, by the way, which is a standard procedure that we do. And if you then calculate it back into some what we call the typical error of the measurement, we see there's a rough error there of about 4.3%, which is slightly higher in the 60%, which is 5.8, and slightly higher in the 50 and the 60s. If we look at relationships between the study, we can see that we had problems finding relationships, specifically in the females. At 30 seconds, the strongest relationships were found at 60s, and slightly weaker relationships at 90s. If we look a little bit closer to that, and we look at relationship between peak power output and RMSSD, we can see that we're finding similar slopes but different y-axis intercepts. So that means there's different relationships between males and females, although over time we've got a similar slope. We again see the similar tendency as well with VO2 max and RMSSD, and with 40k time trial performance we see a similar performance as well. And this might be partially due to allometric scaling and differences in body mass and the difference that we see between male and female cyclists. So in conclusion, with regards to the relationship study, we're finding similar slopes, we're finding different y-axis intercept, which means that we cannot directly combine the two data sets together, but we actually have to differentiate between the two of them. So in conclusion, one more slide actually. If we compare the data between the males and the females, we see similar relationships, not too far apart from each other. We see similar standard error of the estimates as well if we look at the relationships as well. But what is interesting to note is if you compare the heart rate recovery data with the RMSSD data, we're actually finding substantially lower errors of the estimate. So with the RMSSD, we'll be able to get a much more accurate prediction, for instance, of peak power output. So this is with a measurement error of about 12 watts, and this is a measurement error of about 24 watts. So it's about 50% reduction. So it seems that RMSSD might be slightly more accurate in having a relationship with cycling performance, both in peak and endurance performance as well. Conclusions, I think the highest reliability we found in heart rate recovery in RMSSD. The strongest relationships were found with 60 seconds RMSSD and cycling performance. However, we need to remember that the gender differences between those two factors as well, so you need to keep that into mind. And I think one of the things that we can draw from this study is that it seems that we can actually measure log transformed RMSSD after a standardized submaximal test, and I think that the design of this might have added to the reliability of the data as well. We know that the good relationships between RMSSD and cycling performance, however, there's gender specific, and RMSSD seems to be a promising additional parameter for monitoring and fine-tuning training in cyclists. So with this saying, I just want to make the last one, but not the least one. I think we're not going to find one parameter that's going to actually tell us exactly what's going on. So we need to always look, and to be able to accurately monitor and interpret data, we need to collect multiple parameters, and I think RMSSD can be one of them, but you definitely need more, and we need multiple variable analysis as well to have an correct interpretation of this data. Thank you so much.